Thanks, everybody. Thanks for coming back from the lunch break without significant break-off in participants and choosing our talk. We know there's a lot of variety of excellent talks on this conference, and we are honored you choose us. Today, we bring you a topic which is of high relevance to the so-called old economy, which can only be accomplished with you, with the representatives of the free and open source community. We need you. And in particular, we'll bring you a talk about cybersecurity challenges in operating systems for the software-defined vehicle. And who is we? We is basically my colleague, Dr. Rodrigo Docamo of Seconet company. Sadly, he was stricken by a sudden illness and he can't be with you, but I'm trying to make it up to him, of course. And myself, Michael Schneider, I'm the principal expert for product cybersecurity at ADMOVEO. And ADMOVEO is a name which is not around for that long, but you might know Continental Automotive Systems. That is the company which actually, is this company after its spin-off on the stock market last year. So let's look a little bit what we have for you today. And we're starting with nothing less than the attempt to explore why open source might just be the silver bullet to meeting all the challenges of the automotive industry. Then we will be looking at the role of operating systems through the lens, through the goggles of cybersecurity for the safety of the road user, of course. After that, we will try a comparative view on operating systems and their role in automotive use cases, and then nicely finish it off with some insights into the challenge space of harnessing operating systems under cybersecurity aspects and auspices. So let's take a little time to set the stage where we are as an industry and as a society. We all know that we are undergoing steep and grave demographic shifts, and we are moving towards a digitally empowered society. Trends like urbanization, individualization, and the digital lifestyle is, just how our society evolves at the moment, and which also shapes our consumption behavior. And as an industry, we cannot deny that we shape our product offerings to what the market demands. That is what enterprises do. And that's why we are all experiencing the next generation mobility, which is characterized by exponential evolution of technology and technology offerings. We talk about the software-defined vehicle, and when we do that, we mean server zone architectures, edge computing, what have you. And all of this is cloud-empowered, is working robustly, and of course, cyber-secure, because nobody wants to be in danger. And no slide these days can be complete without mentioning AI and virtualization and big data. You just have to have those buzzwords, and they are basically no show. They are really driving our life these days. You all know that. But there's even more to it. The underpinnings of all of those evolutions is a change of our ecosystem on which user behavior and product offerings work as a substrate. We see that we have a lot of new market actors. You see that people and companies from far away continents are entering the market with force, a market that decades ago was more or less firmly partitioned, but today is fiercely fought over about market dominance and having share in it. Slides like this I'm sure you are no stranger, but they are necessary to exemplify where we came from and where we're heading to. So on the very left side, you see what we refer to as the old or the traditional architecture in vehicles, which was characterized by gazillions and a large number of individual electronic control units with their isolated functionalities, and at best there were certain networking connections between the units which shared certain domain functions or had to interact. And on the very right side, you see a projection where this could be heading over time. And this is basically the end stage of a centralization evolution, which is characterized by two megatrends. The one is up integration and domain and zone centralization, reducing the number of individual computational units, and the other one being a radical rearrangement of software, because obviously if you want to keep and contain the software and functionality you had in the past, and you don't want to miss in the future, you have to rearrange it, to repackage it, to refactor it. And as we all know, being software people, that presents a lot of challenges. After this more statical view about what's happening in the inside of the vehicle on architecture perspective, let's look at the software lifecycle perspective a little bit. On the upper half of the slide, you see your past as a vehicle purchasing customer. So in the past, after you have bought your freshly configured car in the car dealership, you only could expect to get software updates in cases where there were, imminent callbacks or were safety or security problems of any sort, major bug fixes. And for the rest of the usage period, more or less, you were left alone with what you had purchased. But then enter the software-defined vehicle, which is characterized by a decoupling of hardware and software using the magic bullet mechanism of abstraction. And what this mechanism does is it allows companies to maintain the so-called middleware in the vehicle over time. And this again presents the opportunity to provide the customer with new function and new service offerings over lifetime. That is what the market thinks, what is needed, and that what we see the customer is calling for. But of course, that requires to do something on the level of the software platform, middleware, and operation system. But I was being uncourteous. I've been using all these terms for which I know there are multiple definitions around, even on the technical stage. And that's why I take a second to define what we will refer to as software platform, middleware, and operating systems. So basically, the platform consists of the middleware and the operating system. And when I talk about middleware, I refer to the part of the software stack which is between the application and the operating system, facilitating mainly data exchange and communication tasks. And when I mean operating system, I mean basically what is between the middleware and the hardware itself. Both very important parts of the stack which have to do with hardware abstraction and also providing new software offerings. So let's take a further look of why we think that there is evidence that open source software might just be the solution for Europe's problems. Just lately, by the European Commission, the so-called ECAVA initiative has been launched, the European Connected and Autonomous Vehicle Alliance. And if we look at the mission statement, you find all the right buzzwords. Autonomous, software-defined, and being geared at competitiveness and technical sovereignty. So, thank you. And if we take a deeper look, we see the individual work packages or items which are part of this initiative, predominantly projects of common European interests and to have input on European regulation. And as I heard many people say on this conference already, when you talk about input and regulation and open source, the CRA cannot miss in this context. And especially on the ORC compliance track, you will hear a lot of these talks, and I am sure they will be very interesting. So all in all, ECAVA is trying to put a nice wrapper around all these seemingly independent initiatives, or in order to borrow the words of Mike Milinkovic today is, we need an umbrella project management for all of what is going on in Eclipse and the software-defined vehicle, and this ECAVA initiative might be just that. ECAVA itself has been suggested by the automotive industry in a white paper, and you will see the link of the white paper on the bottom of the page, so you find that on the internet. I'm not going to read it to you here. And you know, it's interesting to see that this white paper is kind of a dissection at the problems which the automotive industry and supply chain thinks it is facing at the moment. And there are a lot of categories of challenges, but for the sake of brevity and keeping it together in this talk, I only want to focus myself on the software stack and operation system and middleware. And there is the clear statement that inconsistent operating system and middleware building blocks are a huge part of the problem what we are having. And we will dissect this further going forward. Elaborating on the problems we have with the software platform and the middleware is, we have to rebuild the middleware basically from the ground on in every project that we have. We see a lot of OEMs, we see a lot of suppliers, and somehow the industry has the impression we are reinventing the wheel for this part of software, which kind of should be standardized already for decades, but we are still doing it seemingly for every project individually. And here come the open source benefits, which could just be the solution. So in the open source hemisphere, we see shared and open source stack solutions for non-differentiating functions. We see advanced mechanisms for hardware and software abstraction and to create modular software. And we see also industry-wide standards for middleware involving through the participation and evolution of open source. So it's obvious we have problems, open source has solutions, so let's bring it together. And here we're coming back where problem, solution, and initiative meets the ECAVA initiative and what Eclipse does with the Eclipse SDV S-Core project, which in the mind of many participants and representatives of the automotive industry is a crucial initiative that feeds into this overall picture of what we're trying to do in Europe. But, you know, I put it out front. I'm, you know, a cybersecurity person, and so that's where I want to put my point of view and the lens of what I'm looking through. So let's look at all of this through the lens of cybersecurity, supporting property of safety on the road. And what you see here is a first glimpse at, I would say, that's the scope of S-Core. And I talked about, you know, standardizing this whole software platform. And this is what you basically see in the dotted boundary in the middle. That is the scope of S-Core. That is what it is trying to standardize. And it's trying to reach a point where we standardize all non-differentiating software in this stack, where we have working bridges for operating systems and applications, where we have standardized work products and solutions for safety and security in order to deal with the compliance overhead of creating all the evidences and all the work products, where we reach hardware independence, and what's important, because we are a free market, we are leaving nobody behind. No vendor, no supplier, no OEM. This is a democratic solution. In that sense, I basically have to elaborate a little bit that when we see the operating system and the hypervisors in the bubble of the software platform, we still will have operation system and hypervisor vendors, don't get me wrong. It is just that they will be, hidden away under a different layer, which is called operation system abstraction. And that is one of the main topics that I want to treat, or that we wanted to treat in this talk, is elaborate what we should pay attention to when we are abstracting away the operation systems and the hypervisors to make sure that we still have a functioning vendor market in all of this. So why are operating systems and hypervisors so important for the safety and the security perspective? Because they run in privileged and protected modes, and they encapsulate a lot of software which is often used, which is often called system calls. And the operation system governs the scheduling and the interrupt handling, and makes sure that in fail operational systems, like in automated driving, certain applications can fail and can be restarted, while other ones, which are safety critical, keep on going and keep you safe as a driver. Very important. And at this point, we introduce the term of the hypervisor, which many, of course, you know, but for all others, that's basically another mechanism of, for example, running many guest operating systems on the same silicon and creating another layer of hardware abstraction. And the hypervisors, again, they do a lot in the term of safety and security assertions. They help us create freedom of interference, and there's different kinds of that, like, for example, spatial, temporal, and functional freedom of interference, meaning memory protection mechanisms, meaning control flow integrity for the software, and meaning separation of functional concerns with different safety and or security requirements. And especially the hypervisor helps us also keep confidentiality, keep availability of system resources, and helps us to keep our software in the state of integrity. For example, that software cannot be manipulated, cannot be tampered with, and that you have all those assertions which you have also heard of, in the previous talk about automotive operating systems. That, of course, applies to this project too. And what we see here is a first attempt looking at the complete scope of the S-Core project from a functional perspective, showing all the desired functionality as functional blocks on the system level. And what we have done in order to create kind of a scope for what refers to as operation system and hypervisor relevant, we have created this red delineation line, which basically is a boundary box of all the functional concerns which we see as operation system and hypervisor related, having affinity, as we say. And you will see that there are functional blocks which are marked with the shield symbol signifying particular affinity to cybersecurity. And those are the functional blocks with direct security focus. All the others, of course, having indirect cybersecurity focus or exposure. And if you look at the sheer magnitude of this boundary, you see that operation system hypersecurity and security relevance makes quite a lot of the overall concern of the scope of this S-Core project from functional perspective. And so in order to give evidence, for our argument, creating this partitioning, we have looked at hardware abstraction aspects of operating systems. We have looked at the elements of low-level networking, like, for example, creating low-level networking stacks and routing mechanisms. And lastly, we have also looked at functionality for resource and process management. And in the last bubble, one line item sticks out, and that is, for example, the exposure of system call interfaces. And that is basically where the term abstraction, for example, of operating systems, meets a vocabulary that many have used. Also, the last talk about operating systems, which is POSIX. And for those of you who don't know what POSIX is, that's a generalization of operation system functionality, which is around for a long time and which was originally conceived in order to deal with portability needs and demands. And so this term is going to stick with us for a while. Operation system abstraction is important because all the functionality that you have seen will be abstracted through the S-Core project. And what we can see so far is, of course, on GitHub, in the official documentation, we have requirements for the operation system abstraction. And this is fantastic because that is a good starting point. And what we also see is that we have an idea to create this operation system abstraction on the POSIX standard in order to enable POSIX-like or POSIX-based operation systems like Linux and QNX. And also what I found very good and encouraging is that there are also safety assertions or safety requirements tied to this requirement. So it's hard to see on this slide. So I have rephrased it for you as the audience. So explicit requirements coming from what I can see on GitHub are the OS abstraction security concept shall enable safety assertions up to ASIL B. And you have heard that a lot. That's kind of a safety requirement on a scale from QM, less safe, to ASIL D, more safe in very general terms. And the OS abstraction layer shall accommodate POSIX-like operation systems and shall be vendor neutral. But at this point, I like to introduce an implicit requirement, which is not written there, but what I think needs to be injected in order to tell the whole story. The operation system abstraction layer shall address the functional gap not specified by POSIX, but being created between POSIX specification and the aggregate functionality of all operating systems which are on the market. And this is just a selection of a few categories of the specification gap which are basically manifested through evolutions, for example, in the real-time Linux kernel evolution, and between the lack of specification on the POSIX level. And you will find deltas in scheduling, interrupt handling, hardware tuning, timing, and kernel configuration. So if S-Core wants to create an operation system abstraction which is really vendor neutral, which helps the industry, and which maximizes the effect for different operation systems and different applications. This should be dealt with. Now take it, on a more general level. So now that we know that there is a gap, how do we look at the aspects of this gap? What is the good, what is the bad, and what is the ugly? And at this point, I'm not going to tell you all about the line items. I'll just read you the first line, which contains 2 quotes of the absolute fan favorites in the cybersecurity community. So what is the good about the gap? Knowing the gap and knowing that it might be a trap is avoiding it. That is an uncredited quote of Admiral Akbar after the Battle of Endor. The bad is, while POSIX gap analysis is ongoing, security has to work with claims and assumptions. And if you have ever talked to security people, they are chronically critical and they don't like uncertainties. So they always want to know what they're dealing with. And in order to drive this point home, this is the real ugly of projects in their concept stage or in the beginning stage. You can only know what you protect or protect what you know. And this is from Bruce Schneider, the #1 cybersecurity evangelist. So let's now dare to take a comparative view about what today is reality in the automotive industry in terms of mixing operating systems in the same system. So this slide in itself is very busy and would merit a complete talk of itself, but I'm going to simplify the chart in order to amplify my message. What you see here is, from left to right, 4 guest operating systems on 4 distinct cores on 1 silicon. And they all have their own operating system. They all have their tailor-made application stacks. They all serve different purposes, and they have different safety assertions, what you see with the different ASIL levels on the top of each stack. And the operation systems, they will be more or less, in most projects, OEM chosen or be dictated by the properties which are expected. And the applications, they range from applications which are statically installed, for example, on the leftmost core, to quasi-app stores on container runtimes on the second to the left QM core. And to drive this point home, this is what a Kava or S-core has to enable to make sure we can do things like that and even more complex things also in the future. Mixed criticality, let's say driven to the excess, I would call it. So this is no science fiction, this is actually an architecture of an HNI system which is really in series production. So in order to measure the depth of the challenge which this project is facing, we tried to measure the depth of this challenge. And what you see here is an overview chart on the y-axis featuring the most prevalent or more distinctive properties of operation systems, and then on the x-axis a selection of the most prevalent operation systems in use today from our vantage point in the automotive industry. And they are being separated by a thin red line in the middle according to their criticality focus. On the left side, the most highly critical geared operation systems, and on the right side, the ones with intermediate or lower security or safety focus. And of course, there can be debate where the red line should be. But the point we are making with this slide is not to intimidate anybody, it's just to measure how deep is the challenge for the product, to pipe all this functionality and its variance through an API interface of an operating system abstraction without creating attack surfaces or hindering portability and vendor neutrality. So, as it is very uncourteous, or it would be rather uncourteous only to show problems without giving hints for solutions, we have tried to conceive a set of, if you will, best practices or rules, which we have shamelessly stolen and derived from the OWASP top 10 of API security, and tried to reformulate it in the scope of operation system abstraction. And as we are short in time, I'm just gonna pick out a few of those. For example, what we think is essential, that APIs should be strongly contract-driven. It means that between the user space and the operation system, there should be explicit and kernel-enforced mechanisms. Or, on another note, there should be a so-called version minimization, which means if you have the choice when adding a new functionality to create a new version of an old interface, don't do that, rather create a complete new function, or as some scientists say, no mutations in semantics of existing ones. And all of this information is out there. It's basically state of the art. None of this is rocket science, I'm sure, but somebody has to do it, or a group of people with the same goal has to do it. It is just what we need to do in order to fulfill our vision with this initiative and with this project. And if I had only one slide, to drive the point home, or to give, good advice to people who actually, put their finger on the buttons and type source code or tell it to an AI for coding these days, let's make the scope of a project very, very clear. Tell what you do, tell what you not do, and that is very important, because even if the project is too ambitious, and you see you have to cut back explicitly, because then other people can develop better workarounds and make safe and secure workarounds. With regards to the innovation and portability trade-off, that is just the fact in our ever-evolving technology. You have, from the get-go, to plan an ATI to be deprecated, for example, if you bring a product into production. So when you create those abstractions, for example, also plan for the deprecation of interfaces that will, in the end, make the code more secure. And to get back to the specification gap between POSIX and the aggregate functionality of all operating systems, get it documented. There is no way around it. It needs to be explicitly laid down, because then it can be filled with communalized definitions or new specifications that again can be standardized. But overall, all of this is doable, because really, we put people on the moon, and we again made them surround the moon, and the challenge is doable. We just have to know what we protect and do it. And there is an overall positive message around for those who are forced to accomplish those goals in a short time, or have similar goals in their, product development. You don't have to do it alone. There are business partners around, and for example, my company, ADMOVEO, prides itself with having system integration services, tool support, providing developer environments, safe and secure compliance, work products, processes, and consultancy, as well as virtual test environments. And we pride ourselves in supporting the ESCOR initiative and ECAVA, and we hope this is off to a good start, because, to requote Admiral Akbar, to know a trap is avoiding it. Thank you for your attendance.